This is problem A in chapter 8 about the space station, and this is what it says. A space station consists of two donut-shaped living chambers, A and B, that have the radii shown in the drawing. As the station rotates, an astronaut in chamber A is moved 2.40 times 10 to the second meters, or 240 meters, along a circular arc. How far along a circular arc is an astronaut in chamber B moved during the same time? Okay, let's see what we have given here. First of all, we do have given the radii for both of them, so for radius A and radius B. Then they give us the arc length of one of them, and then they ask for the arc length of the other one. We can put these together and actually calculate them as a ratio, or we can determine the angle for the first one, and I'm going to do that, and then of course the angle is the same for either one of them, and then come up with the unknown over here. So the equation I'm going to use is arc length equals radius times angle. There we go. And when I then plug this in here, just one algebra step, and then I plug it in, theta equals arc length S divided by radius. And this is actually all for chamber A, what I'm doing here. And then it is, let's see, 240 meters divided by 320 meters, and that comes out to 0.75, and that is in radians. If you want to know how much that is in degrees, just out of curiosity, multiply by about 50 or 60, so in the neighborhood of, I want to say, 45 degrees. Okay, now for the other one, we use the same equation, so we're going to have SB equals RB, which is given, the radius for chamber B, and theta B, which is the angle through which chamber B rotates, and of course that is the same as the angle A, because the two are coupled together, so it can't move anywhere else, and so you're going to come up with the distance with the arc length S by just plugging in these two numbers. Now I got a follow-up question for this one here. What would interest me is that as this rotates here, of course there is a tangential velocity, which in this case we're not calculating, but that tangential velocity, respectively that angular velocity, gives a centripetal acceleration. Of course it's the inertia that tries to push the person out this way actually, or this way, and then it's a support force by the outer rim of each of these two chambers that pushes a person in, and that's actually the force they feel, and that actually is the centripetal acceleration or centripetal force, which is written as AC equals V squared over R. I didn't mean to make the smear here. V squared over R. Respectively, in this chapter, they show us that this can also be written as R times omega squared. And omega squared is the same as the angle theta divided by t, or actually it's delta theta divided by t squared. Respectively, of course, the centripetal force is mass times that acceleration. Okay, in this case I also don't need the tangential velocity, I just use the angular velocity, except we don't have t. They give us r, they give us theta, but we don't have time t, so I'm just going to make something up, and I make up t equals 8 seconds, and there's a reason why I choose 8 seconds. You'll see that in just a moment. So what I have now is that for the outer rim I have 1,100 meters times 0.75 radians divided by 8 seconds squared, and I'm going to come up with, let's see, 1100 times parentheses 0.75 divided by 8 parentheses squared, and I come up with around at 9.7, and that of course is meters per second squared because it's an acceleration. And you can obviously see why I chose 8 seconds for these 45 degrees that it rotates, because that then would give me the acceleration due to gravity that we're used to here on Earth. Of course, here it's the centripetal acceleration. It's not not caused by gravity, but by the support force of the outer rim. That actually means it's turning pretty fast for a radius of about 1,000 meters, which is a little over half a mile in radius. It's actually turning in, yeah, I think 60 seconds. Yeah, 45 degrees, so 8 seconds for 45 degrees. That means 60 seconds for one entire rotation. So within 1 minute, that's quite fast, I believe. Now for the other one, for chamber A, well, it's the same kind of calculation, except that the radius here is going to be different. So again, it's theta squared over t squared, or in parentheses, and this one here was actually chamber B. I did that first. Chamber A, I do that second. The reason is that we get a larger centripetal acceleration on the outer rim that we get on a smaller one, because the radius here is smaller. And so when I do that one, I'm going to have instead 320 times 0.75 divided by 8 squared, and I come up with 2.8 meters per second squared. So for people moving forth and back between the two chambers, they have to pay attention that they feel kind of the Earth's gravity on the outer rim, but here they feel only like a third of it, or even just a fourth of what they're used to. I wouldn't put the 9.7 on the inner one, because then you get a larger one on the other one. So I believe it's easier to have the smaller centripetal acceleration here than what you're used to, than having a larger one. Anyway, what I wrote here in blue here is just a follow-up to the original problem that I had written in orange.